I've always loved artificial life simulations. How just a few simple rules can combine into something that looks unexpectedly alive. On screen, you're seeing two of my favorites: Boids on the left, particle life on the right. Boids behave like birds, fish, or swarms of insects, each birdoid steering based on alignment, cohesion, and separation. Particle life is totally different, with the species pushing and pulling like digital chemistry or gravity. Both are simple, both are beautiful, but they live in different physical worlds. So I started wondering, what if they didn't have to? What if these two ecosystems could coexist in a single simulation? Turns out you can do that, but it takes a little work. I've covered both of these digital life sims on the channel before, and you can find the full Godot source code and compute shaders for each one on GitHub. But let's look a bit closer at how they work on their own. Boids react socially. Each particle looks around, averages what its neighbors are doing, and steers based on those averages. It steers to align directions with its neighbors, it steers towards the center of the group, and it steers to maintain personal space between it and other Boids. That's it. Three forces, yet we get flocks, swarms, and those satisfying ripples you see on the left. Particle life, though, doesn't care about averages, or directions, or steering of its neighbors. It's all raw push and pull forces between different species or colors that fall off over distance. Species A can repel species B, B could attract C, and C could even ignore A altogether. On the right, you're watching a species interaction matrix in action, a simple grid of numbers that's creating the spirals, clusters, and predators and prey dynamics that you see between the particle life species. These two systems don't just behave differently. One works through steering and velocity, the other through direct push and pull forces. You can't just drop them together and expect them to cooperate. At first, I tried simply adding the forces together, and immediately one system crushed the other. So the first step was getting them to play together in one space. Boids move by steering. They measure how their neighbors are moving, average those vectors together, and nudge their own velocity towards that direction. Particle life does it differently. It doesn't care about direction at all, it just pushes or pulls on neighbors one at a time based on a species relationship. Because these two systems operate differently, one modifying velocity based on averages and the other applying direct forces, they don't naturally line up. Before the two systems can be blended, they both have to be expressed in the same force language. Boids produces three steering components: alignment, cohesion, and separation, each based on averaging the neighbor's behavior inside of a vision radius. Particle life produces a direct attraction or repulsion vector by inspecting neighbors inside a separate interaction radius and applying species-based forces that depend on distance. Inside the compute shader, each agent loops over neighbors. For every neighbor inside the Boid vision range, the shader accumulates the raw alignment, cohesion, and separation contributions. For every neighbor inside the particle life range, it accumulates a push or a pull determined by the interaction matrix and a force falloff. After that loop, the Boid side is averaged and normalized. Each steering term is reduced to a single normalized vector, which is scaled by its corresponding weight setting. The particle life side already produces one combined vector on its own. Now we have two clean, comparable outputs, one vector for Boid steering and one for particle life forces. Only after both systems go through this loop and normalization process do we blend them together with a mix slider. That's the actual moment that the two physical systems come together. We can now control how much of each sim affects the final result. Blending the behaviors was one thing, making it run fast was another. Both systems are expensive to compute. They want to compare every particle with every other particle. Double the particle count, you quadruple the calculations required. That just doesn't scale with a high particle count, even though it works for a small number of particles. So I added spatial partitioning, or at least my first attempt at it. The world is divided into a grid, and each agent will only check its own grid cell and the 8 cells around it. Here's the flow you're seeing on screen. Each particle identifies its grid cell, wrapping around the world boundary at the edges. It only scans a 3x3 block of neighboring cells to loop over. Once that loop finishes, the shader has everything it needs, all neighbor data gathered for the agent for the current frame. Only then does it move on to the final velocity update and position integration. With this partitioning in place, the hybrid simulation moves into near real-time territory. Even on my older NVIDIA GPU, it can handle around 50,000 agents at a reasonable FPS. It's still not perfect, and there's plenty room for improvement. For example, if too many agents crowd into one cell, the cost spikes again. More advanced partitioning may help reduce that issue, but that's a problem for another day. Once everything was running smoothly, I finally had time to just watch. And right away, the world started showing patterns I wasn't expecting. As the mixing slider moves into the middle range, the simulation enters a strange in between zone. On screen, you'll see cells forming, breaking apart, spiraling, and regrouping, almost like the rules are negotiating in real time. Boids start flocking around particle life structures that didn't even exist before, while clusters of species orbit each other and form trails and shapes neither system could create by itself. It's like the simulation discovered a new behavior, one that exists between social steering and gravity. What surprised me the most is how little it takes to actually reshape the ecosystem. I added a bunch of bells and whistles for inputs, but the main settings come down to just a few things. A few species to species values in the interaction matrix, the sensing range for each sim, a couple of weights to control the Boyd forces, and one slider to mix everything together. Tiny nudges to these values produce entirely new environments, sometimes stable, sometimes chaotic, and sometimes something in between. Working with this idea of merging simulations convinced me of something. Even the simplest of systems have personalities. And mixing them isn't just smashing the math together, it's tuning, it's intuition, and it's paying attention to what emerges when you flip a single number. If you're interested in how compute shaders work under the hood in Godot, be sure to check out our other videos on the channel that break down the nuts and bolts of using Godot's local rendering server. If you find odd behaviors in any of these sims, or discover patterns I haven't seen yet, or especially if you have suggestions on performance, let me know. This little world still has a lot of growing to do. I'm already exploring the next steps for the project. Some new force types, better GPU optimizations and partitioning, and maybe even layering in a diffusion system or basic cellular automata to the party. And who knows, maybe this hybrid world could become a small game someday, something like a bullet hell game where you're navigating inside of a living particle ecosystem. For now, though, I'm just enjoying the process of combining these digital life sims, where two very different types of forces manage to coexist and create something greater than the individual parts. Thanks for watching the Pathfinder's Codex. Be sure to like and subscribe, and as always, never stop trying new things.